I'm going to show you, and I hope if you have a laptop, please feel free to follow along. If you don't have a laptop with you, you can get the same data that I'm going to show you at this site here. So at least write down the site, and you can download the data. You can get it at home. In addition, there is a handout right here. Torturing Excel. It's a handout that looks like this that will explain all the things that I'm going to do. I realize that I can only do this talk in English. Perfect. Thank you so much, Laura. I can only do this talk in English, and for many of you, that may be a problem. But again, I think you can follow along at home by going through the same exercises. Okay? So we're all good. Everybody had a chance to write that down? Okay. Let me put that away. Let me make this big. And here we go. Okay. What we're trying to do here is use Microsoft Excel to do work with statistics. And I realize that most journalists don't want to do statistics, but there are some that are useful. In fact, there are some that you do, in fact, use. Things like average and maximum and minimum and so on. Those are all words we use in our stories. So if you've ever written a story where you've talked about the average of something, or the biggest or the smallest, you're already doing statistics. So I'm going to show you how to do things somewhat easy with Excel. Now I will add that Excel is not the best tool for doing this. If you start doing statistical work, statistical studies of data, in a more serious way, you want to get a tool like SPSS, which is it's actually a much easier way to do statistical work. The problem with SPSS is it costs lots of money. There are other choices. In fact, one of the choices that I talk about in the handout is a piece of software that looks like SPSS, but it's an open source, free, and it's called PSPP instead of SPSS. And I have a link for it in the handout. So that PSPP will do many of the same things that the much more expensive SPSS will do. But if all you have is Excel, you still can do lots of interesting things. So let me take you through some of those things you can do. Let's switch to here. Come on. I want that. You want this. Here we go. Okay. What often we want to do with statistics is what's called descriptive statistics. Things, again, like the average and the maximum and minimum. There are a few that we use a lot, and Excel has ways to get that kind of thing. Let me just close this here. Excel has some easy tools to do that. One way is to write Excel functions. I'll do this. Okay. For instance, if you want to, what I'm working with here, what you see up there is actually exports to Argentina, imports that Argentina has gotten from the United States in the last 10 years, dealing with various kinds of military equipment. This comes from our U.S. Census site. It's actually very interesting information, lots of other products, how much wine you send us, how much military equipment you buy from us, that kind of thing. So one of the things you might want to say about say military equipment over 10 years is what's the total amount of money that Argentina has spent on getting military equipment from the U.S. The simple thing would be to add it up, the sum. So you could do this, equals sum. Now this is in, I should add, by the way, what I'm using obviously is the English version of Excel. For you, it might be Summa, is that right? Summa? Okay. That's one thing I learned when I was in Portugal. I was telling my students how to do all this, and they were looking at me like, how do you make this happen? And I finally realized that they were using, obviously, the Portuguese version. So anyway, sum, and here to here. Okay, so the sum from B2 to B11, you can add that up. Whoops, pardon me. 11. Trying to do this one-handed. Here we go. And you get the total amount of just over 23 billion US dollars worth of military equipment sent. And you can do that for the other kinds. Here's military aircraft, launching gear, engines, etc. And you can copy this across. Like that. Okay, so that we have is the sum. Now it works? Which is gracias. Okay, there it goes, perfect. So we have the sum there, and you can do the other kinds of functions as well. In fact, there's several descriptive functions. The ones that are built into Excel already include not only the total, the sum, but the mean, which is the average, where you would add it all up and then divide by the number. The median, which is the middle value, the value in the middle, which is not necessarily the same as the average. Too many journalists use them as though they were exactly the same thing, but they aren't. There's an uncommon measure called the mode, which is the number that shows up most often, but that's not necessarily a good average of the, a good way of describing what the middle would be. So you have the general numbers, these measures of the center, things like the average and the median. And then you also have other kinds of measures about what's called dispersion, how spread out the values are, okay? Ones we journalists are very familiar with are the maximum and the minimum, obviously. And then there's the range, which is nothing but the difference between the maximum and the minimum. In fact, there is no function for range. You just take the maximum, subtract the minimum, and you have the range. And that tells you how far apart those are. And then there are things like percentiles and quartiles. And those are other ways of kind of describing how spread out the data is. Now, all those kinds of things, the standard deviation is another one. The standard deviation is a measure. You will never use those words in a story. Okay? You'll never say standard deviation in a story. Your editor will look at you in horror, like, what does that mean? Okay? It took me a long time to figure out how to make good use of standard deviation, to understand it. And the best explanation I ever got for standard deviation was kind of the average distance of all the values from the middle, from the mean, okay? So it's not the way it's calculated. There's actually another way of calculating the standard deviation, but it's a way of thinking about it. It's actually very good. Kind of the average distance, all of them are from the mean. So the bigger the standard deviation, the more spread out the values are, okay? And a small standard deviation, they would all be very tight around the middle. So anyway, you can write functions, just like I did for sum, that will do all of those things. But with Excel does have something called the analysis tool pack. At least the PC versions, the window versions of Excel have this. How many people here use Macintosh? Okay, you're screwed. Microsoft, for no good reason that I've ever understood, took the analysis tool pack out of the Macintosh version of Excel. There are other ways around this. In fact, even though I'm working with a Macintosh, I run the Windows version of Excel in a parallels window. So I can do it that way. There are ways of getting around it, and in fact my handout talks about some of those other ways. So you Macintosh people, you still can do this, okay? But for the rest of you, let me show you what the analysis tool pack does. To get at it, you have to start up here under the, oops, no, not there, where is it here? Parallel, under File, here we go. You go to Options, so you go to File, Options, then go to Add-ins. Click on Add-ins, here they come. And you see a whole bunch of choices that are add-ins. And the one you want for doing statistical work is this one here, the Analysis Tool Pack. And again, it's all described here in the handout that you can download. But if you take the Analysis Tool Pack and you tell it, go, okay, that puts it in, and in fact it winds up being installed here under Data. So you go File, Home, all the way across to Data, and way off to the right, you now see the Analysis Tool Pack. That isn't installed automatically when you install Excel. I don't know why it's an add-in, but there it is. But the nice thing about the Analysis Tool Pack, if you press that button, you see a whole bunch of choices appear. Many of these look very strange. To be perfectly honest, most of these I don't know how to use. I've never had an occasion as a journalist to use them. If you do, great. You can learn on your own how to do it. I can't help you with those. But there are some that are very useful to journalists. Among those are correlation, which I'll show you in a minute, descriptive statistics, which we just started doing, and I'll show you how to use that here in a second. Let's see, let's scroll down a little bit. Regression is a very powerful tool, and I'll show you that here in a second. And most of these others are less good. A lot of them deal with working with sample data. Okay, the kind of thing that scientists do with experiments, where they've done things like social science, where you survey a group of people, and the problem that you work with when you are working with sample data is that you want to make sure that your sample accurately reflects the larger universe that you're talking about. And so you have to have measures that will show you how likely it is that your sample actually reflects that larger universe. For journalists, we usually don't actually care about that. We as journalists, usually as data journalists, are using all of it. We're not just using a sample. So when we are doing data journalism stories, whether it's about crime or elections or education or things like that, we're not looking at just a sample, we're looking at all of it. So many of these other things like analysis of variance and t-tests and two-sample tests and so on, those are all things that we normally don't even have to care about, so don't worry about those. Okay, so let's go look at descriptive statistics, where I started doing the writing out the sum, and then I could do another formula for the maximum and so on. But with descriptive statistics, you can do it a lot faster. Watch and see. So I'm going to pick descriptive statistics, tell it OK. It wants to know, okay, what am I describing? And I'm going to get everything from here, B1, all the way over to my last bit. So I'm taking all my data, everything from B1 to H1. I need to tell it that the labels are in the first row, okay? And I want to put the information on a new worksheet ply. I want to see it on a nice new blank place. And I want summary statistics, and these things I don't care about. So all I have to do is those things that I have just filled out. I tell it, okay. It thinks, and here's my answers, okay? Now, it looks like a big mess right now, but let me fix these so that they're a little more understandable. So I'm going to, let's do format. I always have trouble with this version of Excel. Hold on a minute here. Here we go. Format. That's probably good enough. Okay. So what we've done right here, notice for each one of our variables, we now have all these descriptive statistics. Okay, we have the average, the mean, in this case of the aircraft aircraft buy, or oh, here it is, the military aircraft. The average expenditure per year is 2.3 billion. Don't worry about standard error. The median, notice how different the median is from the average. The median is 31 million. That happened to be the middle value. The middle value between 0, 1 year you bought nothing, and the maximum, 1 year you bought $19 billion worth, is how it works. Here again is that same total we got, the 23.4 billion, and we have 10 values. So again, very easy to create all the different descriptive statistics that you would want out of it. And it does the same thing for each of the other variables. So here we are on the aircraft launching gear and so on. And here we are with the military trucks and other vehicles and the rockets and guns and all that. So all of those statistics got created just by that one command. Okay, so that's descriptive statistics. Let's see what else I want to show you. I'll mention, and I'll show you more in a second, there is a good use for the standard deviation. And one of the, probably the primary use for the standard deviation is a way to measure what are called outliers. Outliers are data points that are way different than everything else. And in journalism, that's what we're usually interested in. We like outliers. We like the most and the least and so on. We don't care so much about what everybody's doing in the middle. We want to know the ones that are strange, because that's usually where the story is. So the standard deviation, and there's a measure that's called a z-score, Z-score, that is nothing but the number of standard deviations any particular value is away from the mean. A good rule of thumb about outliers is anything more than 3 standard deviations away from the mean can be considered an outlier. Okay, because when data is distributed normally, that kind of bell curve that you've heard about, normally it's like 99.7% of values in a normal distribution will be within 3 standard deviations, 1, 2, 3. Okay, so if something's way out here, that's an outlier, and that's one to take a good look at. Why is it so different? Okay, we'll look at those in just a minute, the z-scores. Okay, so we've used the analysis tool pack to do those descriptive statistics, but let's do something else. Sometimes you want to compare variables. Instead of just looking at individual variables and pulling up the statistics about the individual ones, sometimes you want to take 2 different variables and see how they relate to each other. Do they, as one variable gets bigger, does the other variable get bigger also? Or as one gets bigger, does the second variable get smaller? How closely related are they? Do they move in lockstep, or are they pretty much disconnected? Those kinds of things are important. So let's take a look at this. I had to find good data to use here in Argentina. What I had back home is American football, but I figured you guys would be more interested in what the rest of the world thinks of as football. So these are statistics I found from the World Cup of the top players, the number of matches they played in, the number of minutes they played, the total number of goals they scored, number of assists, penalties, the goals with the left foot, the goals with the right foot. You know, who knew? Certainly this American did not know all those things were important in world football and soccer. But one of the things, when I look at a table like this, which I found on a site, I look and say, gee, I wonder if there's a relationship between one thing and another, okay? And that's the kind of thing that a statistical technique called correlation can tell you, okay? Correlation. There is a, pardon me, there's a number that the computer will produce for you. Yay, hooray. I don't know. It must be the, it's a, that's what's going on. Okay, okay. I thought it was Vuvuzuela's, the, okay. The decibels, they're probably measuring decibels. Good job, okay. Good, okay, well that's good. We need that in here too. Okay, so anyway, we have all this data. I want to know as a reporter, certainly as somebody who doesn't know enough about soccer, are there relationships between these things? Are players who score more goals, do they also tend to score more assists, or is there a difference on those? In other words, are there people whose job is to score the goal and other people whose job is to assist somebody to do that? And the statistics should be able to tell me that. The measure of correlation, the measure of how strong those measures are, is a thing called Pearson's R. Statisticians love to invent measures and have their name associated to it. So there is a statistician named Pearson who created this measure. Pearson's R is a number between -1 and +1. It has no dimension. It's not pounds or kilograms or seconds or anything like that. It's just this measure of correlation. The farther away from 0 it is, the stronger the correlation, okay? A positive 0.9, which is a very strong positive correlation, is just as strong as a negative 0.9, which is in the other direction. The important thing about whether it's positive or negative, it depends on how the numbers vary compared to each other. When two variables both get bigger, that would be a positive relationship. When one gets bigger as the other one gets smaller, that's a negative relationship, okay? But the tightness, how well they do that together is the measure of the strength. And that's what Pearson's R calculates for you. So I'm going to show you how to do Pearson's R for this data all at once, basically compare each of these variables with each other. And you can do that, again, using the analysis tool pack. So I go under Data, go to Data Analysis, and this time pick Correlation, tell it OK. And my input range in this case is B1 all the way over to, let's see, how far do we go on this? I, and then I have to go all the way to the bottom. Oops, hold on a minute. Let's do it this way. Let's do it this way. I usually do this with a mouse, so let me see here. Well, let me see it. Let me do it this way. I could write it in. Hold on. Cancel. Oh, I know what my problem is. I don't have an end key here. That's why I'm having trouble. Okay, so the last row I have is row 117. So that'll help me here. So I can fill it out that way. So I'm going to go from here. Okay. That might have helped, but I'll set that up in a second. Okay, so let me start over on this. So 117, I'm going to Data Analysis, Correlation, from B1 to I117. I want it to go on a new worksheet just as before, and I want it to have the labels in the first row. And I'm going to tell it OK. And that fast, here's what it produced. So let me once again make these more easily understood. Okay, these are my Pearson's R's here. And the way you read this, let me do this to make it more readable. Formats. Now that'll have to be, okay. Goals, assists, penalties. Okay. The way you read it is compare each row and column. So for instance here, assists compared to penalties scored. There's a 0.40 Pearson's R. That's a moderately strong relationship between the two, those two things, okay? Notice all these ones, okay? That's a perfectly strong relationship. As one changes, so does the other. On the other hand, it's obvious because all you're doing with each of those is comparing it to itself. So here, matches compared to matches, 1. Minutes to minutes, 1. Goals to goals, 1. So that's all the ones are. Here are the other Pearson's R's. The strongest one I see, just kind of looking at this, is right here. Total goals to goals with left foot. Does that mean something? I don't know. I don't know enough about soccer to know why, for instance, goals with the left foot is a stronger correlation than goals with the right foot. Okay? I'm not sure why. This is something your sports writers would be able to talk about. But
most of the goals were made with
left foot. Okay, coming from the left-hand side of the thing. Okay, that makes more sense than certainly what I knew about. Okay, you see these others that are in parentheses. Those are actually negative ones, and all of these are very low. There's almost no correlation between penalties scored and goals scored with a head, okay? Or those kinds of things. There's just no relationship between one or the other. Some players have more header goals but have almost no penalties, or vice versa. It's just no real difference on those things. So one of the, not surprisingly, perhaps the strongest thing is right here, the number of minutes played and the number of matches played. Obviously, if you play more matches, you're going to play more minutes, and that's why it's so strong. So anyway, that's how you can very quickly look for relationships between two different variables using the correlation matrix. And again, it will do correlation across multiple variables, just like we did there. If you don't have the analysis tool pack, you still can do correlation, but only two variables at a time. There is a function called correl that will do two variables, but it won't do all of these all at once like that. Okay? There's another thing you can do with variables that are related to each other. Oh, let's see, I did have one other correlation thing to play with. We can try this too. Here's one more. This is more football data. And a whole bunch of different things. Matches, yellow cards, red cards, fouls, and this is by team. So we can see all the different teams that played in the World Cup and a whole variety of different measures there. So let me do one more of those correlation matrices. So once again, I'm going to Data and Data Analysis, Correlation. Let's find out what the last row is here first. Hey, God darn it, hold on a minute. See if I can make this work here. There we go. So let let me drag this down. I'm not used to using these. Okay, so row 33, you had 32 teams playing. So we're going to, once again, go data, data analysis, correlation, okay. In this case, we want not that. In fact, we're going to cancel all this. Go to correlation again. Well, let's get rid of that. We're going to go B1 to LM, I think was the last one. M, what was it, 33. And once again, labels are in the first row. We want a new worksheet ply. Tell it okay. And now we have that same table. And let's go back to here. Make those numbers so they're not quite so imposing. In fact, let's do it so we have negative numbers. Okay. So now we can look at the same thing. Here you can see all the different things that we're comparing here. Okay, so where are some of the examples? Boy, this is not surprising. The number of yellow cards and the number of fouls committed by teams. Okay, the more fouls you commit, the more likely you are to get yellow cards. Curiously, there's not much relationship with red cards. I don't know why that is. Why isn't red card where you get thrown out? Maybe it's because once a player gets thrown out, he's not there to commit any more fouls. So I don't know. That probably could explain it. See, I'm already learning something about soccer just by looking at these numbers. You know, goals for and fouls committed. There's a positive relationship. The more fouls that are committed, the more goals that get scored. The teams that score more commit more fouls, but it probably means they're more aggressive about getting to the goal. You know, so yes, they wind up committing fouls, but you know, it helps because they get close to the goal. Is that a good analysis? Does that work? Okay. And so on. So anyway, just looking at this helps lead you to insight about the data that you're looking at. And, you know, I mean, it's kind of fun looking at sports data like this, but there's all kinds of other places where we would be interested. One of the examples, in fact, I'll show you an example here in a second, where we look even more deeply at relationships between variables are things like the relationship between poverty and school test scores, okay? Do kids who come from rich backgrounds do better in school than children who come from very poor neighborhoods? Well, pretty obvious, but we can show it actually with the data. And using regression, which is what I'm going to talk about now, we can actually account for that difference and then still see how well the kids are learning after accounting for the poverty they face. Okay? So let's take a look at that. I'm going to find the regression numbers. This is a data set from the United States. I couldn't find similar data for Argentina. I don't know if you have that. Do you get school test scores for all the schools in, let's say, Buenos Aires province? No? This is something to fight for. It's a good thing. And getting the levels of poverty, which you should be able to get from your census bureau, for instance. Not anymore? No more poverty in Argentina? No. Poverty's all gone in Argentina. Great, okay. Yeah, that's another whole problem to look at. But anyway, here's how regression works. So here I have 200 schools. Okay, these are all in Pennsylvania area, I believe. And what I have here is the percentage of the children who come from families whose income is so low that they are eligible to get a free lunch meal. Okay, it's a simple measure of poverty, and it's basically based on the family income. So school like this one, this Parkland school, only 4% of the children are eligible. So basically most of the children there come from families that are not in poverty. Compare that to, well, here's a good one right here. In Pittsburgh, 94% of the children are eligible for a free lunch because they, their families are so poor, okay? So clearly we have a real range in this large school district for the amount of poverty that's there. These are the reading scores, the median reading score for all the children in those schools. Normally what journalists have done in the past when we have done stories about how well the schools are doing is we will look just at the median score and we will sort by this. And we will do this particular sort. And so we will say, aha, Victory Elementary School, the best school, 86% score in their median score. That's a good school. And then we would look in the other direction, and we'd say, oh, McKinley-Williams School, only two points. And, look at this one, Lock Allen School, horrible. These are bad schools. The trouble is, also look at these numbers that are associated with those. These are kids from the middle of the inner city, the poorest neighborhoods in this case, Philadelphia and Pittsburgh and so on. And the kids at the other end, they're all living out in suburban areas where the families are wealthy and so on. Is it fair to do that comparison? Probably not, and that's one of the things we're going to look at with regression. What regression is like correlation on steroids, okay? It's stronger. It allows you to not only look for the relationship between the two variables, but actually use that relationship to predict what a school should get as a test score based on the level of poverty they have. And the idea is, are the schools performing better or worse than would be expected based on the backgrounds of the children who are there? We're not saying it's good to have schools with very low scores, but what we're saying is it's perhaps not fair to compare the teachers who are trying to teach kids who come in poor and hungry every day compared to the teachers who get to teach the rich kids who are at home with encyclopedias and the internet and all that kind of thing. So that's what regression lets you do. So let's do linear regression. So I have my numbers here. I'm going to once again go to data analysis, and go to regression and tell it okay. It's a little fancier thing to fill out here. What you are doing is comparing what's called the dependent variable and the independent variable. The dependent variable is kind of the outcome, pardon me, and the independent variable is the one that predicts the outcome. So in this case, the poverty would be the independent variable. It's the thing that affects the dependent variable, which is the reading score, the median reading score, okay? How do you know which one is which? Usually the chronology is what will tell you. In other words, it makes sense that a high level of poverty will affect a reading score. It doesn't make sense that if a child gets a bad reading score that their family will suddenly become poor, right? So you look at the chronology. So in this case, our y range, which is going to be, the y is usually the dependent variable. So our y is going to be reading score. So it's going to be D1 to D201, okay? And our independent variable in this case is the low income percent, so that's C1 to C201. Once again, we have labels, so we tell it that. And to do this first one, I'm just going to leave it at all this. We don't need confidence levels and all that kind of thing. So we're going to put it again on a new worksheet ply. I'm going to tell it OK. And it produces this. Okay, whole bunch of numbers and words that are scary. What do all these mean is what we're concerned about. But there's actually only sort of 3 numbers that are on here that we really care about. It's this one here. Let me mark these, in fact. It's that one, which is called R squared. I'll explain that in a second. And then these two right here. Okay, the intercept and the low income percent. Okay. R square is it's nothing but R. Remember we were talking about the correlation coefficient before, Pearson's R. And there it was. In fact, the next number up is 0.81. That right there tells you there's a very strong relationship between poverty and test scores. Very strong relationship. What R squared does, it can be interpreted as the percentage of the amount that each of the different test scores vary from the average. In other words, if you didn't have regression and you were asked to guess the test score for any school, any of these 200 schools, and you were asked to do it over and over, the way to have kind of the lowest error on all those, to add up all your errors in guessing, the best way you could do it would be to just guess the average every time. Okay? Whatever the average is, you guess. Average, guess that. But you would have a lot of error because some are higher than the average, others are lower than the average. What regression lets you do is minimize that error. And what the R squared does is tell you what percentage of that error, of the variance from the average, is explained by that independent variable. So what this is telling you is 67% of all the variance of all those school test scores from the average for all 200 is explained just by poverty. That's an extremely powerful, socioeconomic indicator. It also tells us another third, another 33% of the variance is explained by other things. Okay, and we don't know what they are. We don't have variables for those. They could be things like the quality of the teachers and the interest of the parents in making sure their children do their homework, and 100 other variables. All that stuff goes into the other third. But just the poverty alone is enough to explain a lot of the fact that some schools do very well and some schools do not well. Okay? So we have the R squared, and then we have these two numbers. And what these do is you use these to create an equation that can be used to predict the values for each school. Okay? The way that equation works, you may remember from probably junior high school, perhaps, the formula for a line, y equals mx plus b. Anybody remember that? You may have expressed it in other ways. It looks like this. Let's see, y equals m times x plus b. That look at all familiar? Okay. Another way of doing it would be, in this case, what the formula really is score equals predicted score. Let's do it that way. Predicted score. Let's see, O-R-E equals 71.2 times poverty plus, minus, no, I did that back. I beg your pardon. I'm doing this backwards. That's wrong. Equals negative 0.607 times poverty plus 71. Okay? So this is the formula that you create. Here's our low income percent here, and here is what's called the y-intercept. It's the place the line goes across the y. So with this formula for any particular value for a school, we can predict. Oh, thank you. I have no idea why it decided to shut down, but let's stop it. No, don't. They may have to, because it looks like this thing has decided it's not going to work any harder, and I have no idea why. Okay, well, that's a good idea. The point on regression, and basically if you put in that formula, you would create a predicted score for each school, okay? And then you take that predicted score and compare it to the actual score, and you get something called the residual. And the residual is how far above or below the predicted score each school gets. For some schools that even if they had a lot of poverty, they would have a good residual. They would have a positive residual. What that would mean is the teachers in that school apparently were doing a really good job with the kids that they had. They were making, the children were doing better than expected. And you may find at some of the rich schools that the schools aren't actually doing as well as would be expected based on the background of the kids. When we did this kind of analysis of the schools in Miami, what we found, it was very interesting. We did find, rich suburban schools that had always scored very high, but still weren't scoring as high as you would expect based on the wealth of the children. And at the same time, there were, schools in the inner city, some of the poorest parts of Miami, who were doing better than expected. And so when our reporters went to those schools, what they found were, teachers who were very dedicated, innovative programs, those kinds of things. So what the regression analysis let us do is actually led us to good stories. And that's basically the idea behind this kind of analysis. So you can do that regression analysis and have it basically lead you to good stories, and do these, and it will produce the standardized scores and the the regression and all those other things that are useful. Let's see. Was there one other thing I was going to talk about in here? I don't know what prompted it. Oh, I know. It decided it had to update everything all in the middle of this. Let me show you just one other thing about that data that I can do here in the Mac side of this. One other good way of looking at this kind of data is with a scatter plot. And let's go to regression, and let me set it up that way. So here, if I take this, do all these, and go to charts, and where are my scatter plots? Hey, God. Here we go, scatter. Scroll back up. Okay, here is that data as a scatter plot. You can see, here are the schools with low poverty, and the reading scores are high. And as the poverty increases, the reading scores are going down. Okay, so that shows it. And the fact that they're all clustered together tightly shows the strength of that relationship. The really interesting places are like this. Look at this school here. Okay, has very high poverty, but the reading scores are high also. Why did that happen? What could be going on there? It could be, maybe it's a magnet school where only the really smart kids, even though they come from poor families, get allowed to go to that school. That could be it. Unfortunately, at least in the United States, one of the things we discovered is after a program was started called No Child Left Behind, which created bonuses for teachers in schools where the scores went up. What could possibly go wrong with a program like that? Cheating, okay? We discovered by doing these kinds of analyses that many of the schools that were doing suddenly much better, particularly comparing last year's scores to this year's scores, you would expect them to be pretty close. But there was, all of a sudden, after No Child Left Behind came along, there were schools all over the United States that suddenly were doing much better. And newspapers like the Dallas Morning News, the Atlanta Journal-Constitution, finally USA Today did a big national study, and we found, again, schools, hundreds of schools all around the United States where teachers were going in and changing the tests that the students were taking. Even organized, you know, it was like after school, all the teachers would sit down in a room with all the tests and go through as a group changing them. Well, this of course has led to trials and all kinds of things. But it was discovered, thanks to reporters using tools like these to say, what is the chance that those schools suddenly could be doing so well? The data won't tell you that they're cheating, you know, and again, it could be perfectly on, you know, maybe they suddenly got better. But sadly, we discovered by doing other reporting that lots of cheating actually was going on. So that's, to me, a good example of the kind of thing that can be done using good statistical analysis. Let's see. There was, you know, one other kind of thing. Is that enough to do that? Okay, yeah. Any questions I can answer about this right now? I know. Yeah. It takes, well, if you think about it, I've given you the kind of the best statistical things to work with, the only ones you really need to know. You don't have to know all that other stuff that's under there. The kind of those three things: descriptive statistics, the regression and correlation, and there's a handout, a 12-page handout. So I think it'll take you an hour to learn how to do all that. Okay. You don't have to go take a course in statistics, because if you take a course in statistics, they will want to teach you all those other things that social scientists need to know how to do, because they're always working with sample data. And we're not, okay? We're working with all of it, you know? It's you know, if you were a social scientist and you were trying to study the relationship between poverty and test scores, you might get a sample of 100 schools, or not even 100 schools, 100 children's test scores, and then check the poverty level of those 100 children. And then you would have to do those other kinds of tests, like analysis of variance and so on. But in our case, we don't do that. We just go, we do a public records request, give me all those records. Or we go to the World Bank site and download everything for all the countries in the world, and so on. So a lot of those kinds of statistical tests that really look scary to me too, because I never use those. You don't have to know how to do those, okay? But learn, you know, average and median and maximum and minimum. Right there, you're doing statistics. Play around with correlation anytime you have a collection of variables, you know, whether it's soccer or anything else, you know, crime in your, you know, the number of crimes. Of course, I'm sure you can get that here in Argentina, the complete list of the number of crimes right down to the neighborhood. No, okay. Well, that obviously is what open data is all about, and so you and La Nación can keep fighting for open data, because that's really what you need to be able to do this kind of thing. Any other questions I can answer? Question? Yeah? PSPP? There's SPSS, which is expensive, but is free. PSPP, okay? Pay, is that the right way to pronounce it? Okay. It's free. Just Google PSPP and you will find the site, and you can download it and be doing, you know, in fact, much easier statistical analysis. SPSS, PSPP have nice menus, and they make it a lot easier than Excel does. I mean, that's why I call this torturing Excel, because it's harder to make Excel do these things than other programs are. Other question? Anybody? Okay. Thank you for your attention. Okay.